Hi, Science Nines. I want to now go through the notes explaining electric motors, and as well, I want to talk about power and efficiency. So, to start with, I've added some terms already, which you can add to your notes if you want. We need to know the parts of a simple electric motor, and I've already labeled them here for you, but we'll just maybe connect some arrows. The stator is the permanent part of the electric motor. So it's the part that doesn't move. Hence, the state is like stationary. Um, and we'll look at the DC motor first. So we have a north and south pole here for a magnet, and that's the stator. The armature is the part that rotates. So I'm going to maybe just kind of connect the dots here. So this is the armature, the loop of wire that rotates. Um, To enable it to rotate, we have to use a split ring commutator, and that's connected to this ring right here, which has a split in it or a separation in it. Okay, and that'd be easy to tell if you're looking at it from this side. And there's some brushes. Now, I know your drawing isn't really good, but these brushes are what I'm kind of coloring in right here on both sides. And those are connected to the power source. We just have a little cell right here. Okay, so yeah, so the brushes allow contact from the power source. Now, if you saw in the video before, this loop of wire will only rotate half of a turn because, and if it'll help you, it's as if when you run current through the wire, it's as if this part becomes a south pole and that part becomes a north pole in this drawing. So what that means is initially these guys are going to repel. So the south pole goes this way and the north pole goes that way. Okay. But if you can imagine in your mind, once this loop it gets all the way over to here, now you'd have a south pole and a north pole, and they would just be attracted to each other and it would stop spinning. So the way we get around that is every half turn, what we do is we change the direction of current flow, which will also change the polarity. So this south pole, once it gets over here, what we do is you switch the current flow and then you make that into a north pole, because if you change the direction of current, it'll flip. And then these two guys will get repelled and then that guy will take off. And the same thing will happen on the other side. So that's really what this emphasizes right here, is every half turn the current must change direction so that the loop will keep spinning. Now, if we just slip over here to the AC motor, the stator here are still the two permanent magnets. That's not surprising. The armature is this part that's going to spin. And what's different with an AC motor is we have a slip ring commutator instead of a split ring. So here are the brushes in yellow. You can see them right here. And they're tied to an AC source, so alternating current source. So as in the other one, see here with our power source here, it only sent current in one direction. So the current would only go from negative to positive. That would be the DC part. But in the AC part, the current is flowing in both directions. Well, I mean, it changes direction. I'll maybe change color here. So initially, the current might flow this way, but then it changes direction and it goes back the other way. And so it's going around the loop and then it's coming back. So in the course of changing directions, I'm just having fun here. The change in the polarity of, say, maybe this side being a north pole and that being a south pole, that flips every time the current changes. So in simple terms, the AC motor doesn't need a split ring. It just needs a slip ring. It just needs connection to the power source. And because the current's already changing direction, then you don't have to worry about that. So those are the two differences between an AC and a DC motor, and you should know the parts of each one. Another device that we use to actually control electricity is something called a transformer. Transformers are really clever because often when we're transmitting electrical energy to your home, we have to step up the voltage by quite a bit, because a higher voltage transmits better through the high voltage power lines. You maybe heard of those before. A lot of those are, you see them, the huge pylons that are, out on the highways and whatnot. And even some of them are actually coming to your homes. So what happens here is Michael Faraday figured this out. If you look at this, let's focus in on this one first. So what happens is you bring electrical current in, and then as you can see here, we have just a few loops. This would be a low number of, I would say, turns or loops. Okay, so you have a low number of turns on one side of this transformer. The transformer is really coils of wire wrapped around an iron ring. So see this iron ring here actually will help transfer or change the amount of voltage in a circuit. So we have low voltage coming in, and then what Michael Faraday figured out is if you wrap more turns of wire, so, or you could say high number of turns on this side. So you can see there's a whole bunch of coils, 1, 2, 3, 4, 5. Anyway, there's a whole bunch. Okay. And this is insulated wire, I should say. So it's not like the electricity is just transferring itself directly through this iron core or this iron ring. But what you need to know is that if there's a high number of turns, that produces a high voltage. I don't think that's too difficult to connect. Low voltage is low number of turns. High voltage is high number of turns. So this is called, and I apologize, I typed that right over. This is called a step-up transformer. And what it can mean is, in a simple example, we could go from, say, 120 volts. We could step that up to 500,000 volts. So we could write that as kV or kilovolts. And that's actually a standard, 500 kilovolts is a standard high voltage power line. So those are the ones that are super high in the air. And you might see them as you drive the highway from here to Calgary. There's a couple of stretches where you can see those. So the opposite of a step-up transformer is a step-down transformer. And this is literally what happens after you've done this step up. Basically, when we generate electricity, we tend to generate low voltage, but then using a transformer, we can step it up, and then it's transmitted over the power lines to your house. But you don't want 500 kV or 500 kilovolts of voltage coming into your house. It would destroy all of your electrical devices. They'd all explode, basically, catch on fire. So we safely step that back down, and we do just the reverse. So it's a really unique setup. For here, on one side, you would have a high voltage coming in, which is a high number of turns. I won't rewrite that, but you can see them all there. That's a high number on the left. And then on the right, there's just a low number. So that produces low voltage. And this is where we can go from, like, we can do the reverse. And this is what happens just before your house. And if you pay attention, at least in the rural communities, it might be a little more obvious. In certain parts in town as well, you'll see it's like it looks like a garbage can. It's like a metal garbage can that's stuck to the power line or the posts way up high. You'll see that wires are coming from the transmission lines, and they're going into that box in one way, and then they're coming out of the box in another way. It's exactly what we just described, and that it's taking a high voltage. It may not be 500 kilovolts, but it's going to be a much higher voltage, and it will step that down to 120 volts. So you actually it isn't 120. I just realized it's 240, but because that's the maximum voltage you can get in your house. That's actually what your stove and probably your dryer use, is the maximum voltage that's coming into your house. Your standard outlets only have 120, which is half that. But anyway, so that covers the motors and the transformers. So you need to know both of those functions. So what we want to shift to now is the formulas for power. So first off, what you need to know is that energy can't be created or destroyed. That's the conservation of energy. You might have learned that in previous science classes. But what's neat about energy is that it can be converted from one form to another. We do this all the time. We take electrical energy, we convert that into mechanical energy, or we take electrical energy and convert it into light energy or sound or anything. So, but the rate that we do that is called power. So you can see it listed here. It's the rate at which energy is converted or consumed, and it's measured in watts. So a watt is actually a joule per second. And that's on most of the tests and quizzes I'll give you just to remind you, but you're probably familiar with the easiest one is a light bulb. Most light bulbs are rated at a certain wattage, is how we would say it. A 100-watt light bulb uses 100 joules of energy every second. So what you need to familiar yourself with are two formulas that deal with power, and they are power is equal to current times voltage, or you can also say that power is equal to energy divided by time. And for some quick practice, I'm going to actually switch documents here, and I'll do a couple of these with you because this was one of the practice questions. So let me rewrite these formulas again. So actually we'll rewrite them as we do them. So question number 1 says a generator consumes 15,000 joules of energy in 5 minutes. How much power did it produce? Well, power is represented by capital P. And if I have energy and I have time, the formula that will work for me is energy divided by time. So in this case, I have the energy, and whatever that number is, use it. Sometimes it can be really large because a joule is not a very large amount of energy. It's quite small. So if you have 15,000 joules of energy, what you need to catch, though, is that a watt is a joule per second. And so you can't use minutes. If you ever see minutes, you've got to convert them into seconds. So 5 minutes, if you know there's 60 seconds in 1 minute, so we basically just need to multiply 5 by 60. And I showed you this as a unit conversion fraction. I like to show you that the minutes will cancel out because we don't want minutes, we want seconds. But if you just remember there's 60 seconds in a minute, then if you have 5 minutes, you just times that by 60. So that gives you 300 seconds. And when you do that calculation, 15,000 divided by 30, you get 50. And what you need to remember is that that is 50 watts. Okay, so the units for power again are watts. Now I'll look at the next one because it uses the other formula. So this one says a toaster is connected to a 110 volt power source. That is voltage, and there's 6 amps of current flowing through it. So how much power is dissipated as heat? So if you're trying to calculate power and you're given voltage and current, now the formula is P equals I times V. So the math here is pretty straightforward. We'd go 110 times 6 to give us 660 watts. But what I want you to see here is when you multiply a current, or you multiply amps and volts, that we actually get, I'm actually going to make some space here because I want you to see what that looks like. If we multiply an amp times a volt, an amp, if you remember, 1 amp is 1 coulomb of charge per second, okay, passing a point in a wire. But if we multiply that by by a volt is a joule per coulomb. Okay, so when you multiply a an amp times a volt, there's coulombs in the top and coulombs in the bottom. So they both cancel out. And you're left with a joule per second. Look at that. What is a joule per second? I know you're just learning this. That's a watt. So calculating power, if you're given current and voltage, you just got to multiply those two together. So, and that's just what we did, of course, in question number 2. So let's just finish question number 3. If you have a light bulb that has 1.25 amps and the voltage is 120, how much power does it produce? Well, we would do the same thing. Current power is equal to current times time, or current times voltage, and that would give me 150 watts. Okay. Oops. And if the generator then runs for, oh, whoops, I forgot a 0. If the generator runs for 5 minutes, how much energy will the lamp convert into heat and light? Now, this is one of the variations that we need some practice on, because if you're trying to calculate energy, power is equal to energy divided by time. But if you want energy, you need to get rid of time. The way we do that mathematically is you multiply the right-hand side by t, and what you do to one side, you do to the other. The t's will cancel on the right-hand side. I showed that already. And you're left with a new formula. Energy equals power times time. That's also on the original notes if you caught that. So in this case, to solve for energy, we take the power that we had from the previous, our previous calculation, 150 watts, and we multiply that by, oh, here's 5 minutes again. Can't use minutes. So we have to convert that into seconds. We've done that before. So I still have 300 seconds. And sorry, you maybe can't see that. I need to slide this over. That gives us 45,000 joules of energy. Okay. Now, 45,000 joules, if you have 1,000 like that, you can divide that by 1,000 and express that in kilojoules. So this could really be 45 kJ, like that, 45 kilojoules. Hopefully you can see that. Okay. So at any point in this video, if you need to rewind it or rewatch it, you sure can, but I wanted you to see that very quickly for power. Let's go back to the notes, and I'll let you answer these questions like 1 through 5, because those all deal with, and I'll post the answers to that later, but I want you to practice doing those. What I want to focus in on is the last, actually, I'll show you 2 more here, but we're going to focus in on this formula for efficiency. Efficiency is a measure of how much useful energy comes out of a process based on how much you put in. So your formula, or the one that you'll tend to see, is this one that's noted right here. Efficiency is useful energy output divided by energy input times 100%. So in any mechanical process, you never get 100% efficiency. You can come really close, but experience has shown us that we always lose energy to heat and friction, air resistance, any of those number of things. You won't have 100% efficient. So just know, if you're asked to calculate efficiency, for one, you'll never get an efficiency greater than 100%. It's impossible. And actually, if you do that, then you realize you've flipped it. You've got the input over the output. So it's always output over input. So if it helps, some students like this second version, so I added it. We can rearrange this so it's actually set up as just a fraction or an expression of fractions. And what that means is you can set up your efficiency calculations like this, such that if there's an unknown, like say you don't know what your output is, but then you know the efficiency, you know that obviously efficiency is measured in percent. I didn't say that before, but it'd be efficiency over 100%. And let's say you knew your input. If you knew the 3 variables and you're trying to find the 4th one, you can just cross multiply and divide. I know you guys have done that already in some of your math. Setting it up this way might be a little simpler if you wish, but the the first formula will also work, just that the one I put a box around is a helpful adaptation. So I want to do just one of those with you. I'll do number 7, and then I'll let you try number 8 on your own. So number 7 says, what is the efficiency of a table saw that has an energy input of 1.25 kilojoules and an energy output of 250? This is going to be my input, and this is going to be my output. Now, some students will do this quick. They're like, oh, okay, easy. Output over input, no problem. I just got to go 250 divided by 1.25. That's not correct. What I need you to see, and some of you may have already caught it, is that the units are not the same. We're dealing with 250 joules, and this is the 1.25 kilojoules. Those are not the same units. So what we have to do is make those units the same. And as I noted up here, there are, oh, actually I didn't with joules. Joules, actually all units, if you have a K in front of it, that means 1,000. So we could add up here, 1 kilojoule is equal to 1,000 joules, okay? Just like a 1 kilowatt is equal to 1,000 watts. Knowing that ratio will help you keep the units the same, and I'll come back to this here, because what we can do here is I can change, I mean, for me, I change kilojoules into joules. That's the easier one for me. You could also convert the joules back into kilojoules. They just have to be the same units. So I'm gonna take this and times it by 1,000, because there are 1,000 joules in 1 kilojoule, if that helps. So then this is really 1,250 joules. That's important to catch before you do the calculation, because I don't think the calculation is too difficult after you've seen that. Because to calculate efficiency now, I would just say EFF. That equals the energy output over the energy input times 100%. And I will replace the output with 250. I'll maybe just write that up here. And the input, let's make some room for that. The input will be 1250. So 250 divided by 1250, that's going to give me 20%. Well, actually, it'll give me 0.2, but then you times that by 100, and you end up with 20%. Okay, 20% efficient. Okay, so actually, there is one more that we need to do. So I'm going to actually clear this off. And we need to look at calculating something that we call energy, or that in terms of calculating energy. You won't have to do this very often, but I may have a question or two that deals with what's called the price of energy. How much does it cost? So I'm going to maybe just write that up here, the price of energy. Not that you need to do that, but this question number 6 requires you to do this. So it tells you, in number 6, how much power in watts the air conditioner is using, and it also tells you that it runs for 10 hours a day for the whole month of August. So that's 31 days. Okay. But the question is, how much energy is used? I know we measure energy in joules, but I want you to see that power companies find that joules are really, really small amounts. And so instead of dealing with energy in joules and seconds, like it shows right here, instead of dealing with energy in joules and seconds, they deal with energy in what are called kilowatt hours. And the way that they get that is it comes from this equation right here. Maybe I'll just zoom in on this. It comes right from this energy calculation. What they do, power companies, they measure their power not in watts this time, but in kilowatts. So if you can get your power into kilowatts, And instead of measuring your time in seconds, this is the only exception that you'll ever deal with. Like you always deal with seconds unless you're dealing with this specific calculation. Instead of the time being in seconds, you get the time in hours. And you can see here, normally you would have power in joules and the time in seconds. So a joule times, the power would normally be in watts and the time would be in seconds. So if you multiply a watt times a second, that gives you a joule. In this case, though, the power is in kilowatts and the time is hours. So the energy just becomes kilowatt hours. Okay, we just call it kilowatt hours instead of joules because it's not a joule. So doing that, power companies get the amount of energy in kilowatt hours, and then they just charge you so many cents per kilowatt hour. And so in this question, it says how much does it cost to run the air conditioner all month if you're being charged? I guess it looks like they're charging us 12.5 cents per kilowatt hour. Okay, sorry. So it wants to know what will the cost be. So for questions like this, the first thing you do is you have to determine energy in kilowatt hours. That's probably the hardest part from this, because the second step is just once you get it in kilowatt hours, then you just multiply it by the charge. In this case, it's 12.5 cents for every kilowatt hour. Okay, so the second step I don't think is the hard part. It's like, okay, well, if I have 100 kilowatt hours, I just got to times that by 12.5 cents. But getting the kilowatt hours is the tricky part. So what we do is you've used this formula right here, E equals PT, and you just get your power into kilowatts and your time in hours, and then you multiply those two together. So let's do that for this one. I have 2,000 watts is my power. I'm going to turn that into kilowatts by dividing by 1,000. Okay, because there's 1,000 watts in 1 kilowatt. So 2,000 divided by 1,000 is 2. So what I have is I have 2 kilowatts of power, and what you need now is the total time in hours. So if it was just for one day, I'd have 10 hours, but I'm running it for 31 days. So if it's 10 hours a day for 31 days, that means I have 310 hours, or I call it 310 hours of running time. Okay, so that means then that for my calculation for energy, the total energy that I have for step 1, it's going to be 2 kilowatts times 310 hours. So that gives me the 620 kilowatt hours. That's the amount of really electrical energy that I would have consumed to run my air conditioner. So now I just go to step 2. Now that I've got that, which again, I think that's the harder part. Here, then you would just multiply that by 12.5 cents. Sorry. Per kilowatt hour. And lo and behold, that gives us 7,750 cents. Okay, but in a bad pun, you can say, well, that doesn't necessarily make sense because no one really charges you in cents. They charge you in dollars. So if you remember, there's 100 cents in a dollar, like there's 100 centimeters in a meter, 100 cents in a dollar. So if we divide that by 100, that really means you take the decimal place and you move it over 2. And maybe I'll slide this up so you can see that better. And that means that you could also express it as $77.50. Okay, so there's a couple that's one application that you might see, and I know I just did that for your practice there, but if you might see a question like that is a kind of an extension of calculating the price of energy. So anyway, I hope that's helpful. I'll post another video later on the last part, which is section 4 on energy. But for now, I'd like you to see if you can do these practice questions 1 through 8. now that I've done a couple of those for you. So all the best.